All right, so solids number 7, volume of pyramids and cones. All right, pyramids. When you hear the word pyramids, what do you think of? Egypt, right? Okay, that's pretty good. Have anybody been there? I haven't either. I'd like to go though. That'd be fun. Okay, if you take the pyramids in Egypt and you pick them up off the sand and you look at the bottom, what shape do you see?
Square.
Square. What do you know about a square?
It has 4 sides.
Good. Good. What are the angles in the corners? Right, all around, right? All pretty good. Okay, that's good enough for the moment. So let's start with that. Let's go, okay, ready? Let's see if I can draw this. All right, that's my square, but you're not looking at it straight on, right? You're going up like this, and you're looking at it from the side. So up here's the point. Kind of? Oh, I missed it right there. All right, there you go. There's my pyramid. And like you said, it's a square-based or square bottom pyramid, right? There's another shape with another name where you can have a triangle at the bottom. And actually, there's one where you can have a triangle in here. You can have a triangle like this, and then a point above it, and then a point below it, and it's a tetrahedron. I always thought it was cool. Tetrahedral. Or maybe a tetrahedron is only with a 3 base. Anyway, let's go on with this. So let's talk about finding the area of the base of the pyramid first. If this is the base of the pyramid, and it's a square, and the length of this side is S, how long is the length of this side? S, because they're all the same length. Let's kind of go back through again. What is volume? I know your answer.
Space in a 3D object.
Space in a 3D object, right? Space. Use the word space. When you hear space, do you think of like outer space? Do you think of like space in this room? Okay. Do you think of like space in the glass as you're pouring milk? Okay, I think all those are good, but what's the word we're constantly using, right? This word of space. We use space for area, for the space in a 3D shape, right? Once we use the word area, we're switching. What are we switching to when we use the word area? Length times width. How many dimensions is that? The 2 you mentioned are the 2 that they are. Fair enough? So I'm going to put 2D here. So area is the name of a 2D situation, and she said length times width. S times S. Once you know it's a 2D shape, your brain can start to formulate its own area formula. I guess derive. You can derive or create your own area formula. What's the area formula going to be for the square? What's the area formula going to be for the square? What's the area formula going to be for the square? First, how many dimensions is it?
2.
What are the 2 dimensions of it?
Or no.
Well, can you call them different things? Right? Can you call the 2 dimensions different things? Is 1 dimension this way, and is 1 dimension this way? We can call them different names. So if you took the dimension this way, and you multiplied it by the dimension this way, because it's 2 dimensions, right? What would I write here? Length times width. We're calling length S, and we're calling width S. So now what do I write?
S times S.
Or, fair enough. Hence why they call things to the power 2 squared. That's where it comes from. It comes from because you're finding the area of a square, and you raise it to the power 2. So anything raised to the power 2, you can say S squared, right, instead of S to the power 2. Okay, good. So that's the area of the square at the base. Now, all we need to is go a little bit further with this. We're going to multiply by the height. Here's the height here, H. What can you tell me about H of these solid shapes? What do you know about H, the height of the solid?
Perpendicular height.
Good.
Altitude.
So 90 degrees. Good. You know exactly where I'm headed here. Perpendicular. Altitude. Excellent. Altitude. All right, H. And therefore, if we come over here and I try to get this right, let's see if I can do this. So instead of the point of this thing being here, I'm going to move it over here. And that's about the same height. I'm trying to make it, maybe a little bit higher. So here, 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 and here. Does it look like it is slanted or the top pulled over from the base to the side? And what's your name for this type of shape?
Oblique.
Oblique. I love that word. I don't know why. Everybody say oblique? Oblique. Okay. So, and this H comes straight across here, right? So what I'm trying to do is make these the same thing, H, because we're going to run this idea of volume for this. So imagine we're filling this thing up with a liquid, milk or water, or I guess gasoline. We're trying to fill if our tank in our car were shaped like a pyramid, we'd want to know how many gallons fit in our car, right? Our car tank, that would be a volume. So the volume here for a pyramid is 1/3 the area of the square base, so S squared, times the perpendicular height, H. And if this square is the same as this square, and this H is the same as this H, then the volume for the perpendicular shape is the same as the volume for the oblique shape. Oblique. There we go. And it's 1/3 area of the base times the height. And if we put some numbers in, which is interesting, I was looking at this. Look at this problem here. Do you see the answer to it? Can you see it from way over there? I think it's wrong. So we said the base is 6 meters and the height is 10 meters. So the distance here, from here to here, is 6 meters. And the H is equal to 10 meters. So we said V equals 1/3. 6 meters, we'll put the units into and square it, times the height of 10 meters. So we get 6 times 6 is 36. And the meters become squared also. Squared. Still times the 10 meters. And there's a 1/3 out here. What is 1/3 of 36? 12? 12 times 3 is 36, so 36 divided by 3 is 12. 12 times 10 is 120. So the volume equals 120. And we multiply meters squared times meters to the 1 power and get meters cubed. Is it a good thing that we have meters cubed? Right? And how do you know how to build the formula? We better see 3 dimensions being multiplied by each other, right? We better see that happen because it's a 3D shape. All right. And anyway, do you see what I'm getting at right here? Okay. Now let's roll on to the cylinder. Let's go ahead and do the same thing. Here's my cylinder, like this. I'm going to try to make it the same rough height, I guess. Here. There's an oblique cylinder. Here. And we'll put this off center like this. These things are still running the same H all the way across here. H. All right, and so, oh, what's the area of a circle? What's the area of a circle? Where's the R from here to here, right? The radius. This is going to have the same radius. We'll give them all R. 1/3, the interesting thing about these two shapes is they both have the 1/3 in front of the area of the base times the height. It's the same thing given the oblique shape, V. And so all you're switching out between the two are the area of the bases. The area being s squared for the square and pi r squared for the circle. Do we do a problem like this? We do 6 meters. Oh, I did the same one. That's interesting. All I've got is a pi in there. So V, so we say R equals 6 meters. We say H is still 10 meters. And we say 1/3 pi, 6 is 6 meters squared times 10 meters. 36 meters squared. 1/3 of pi times 36 meters squared times 10 meters equals 36 divided by 3 is 12, 120, but we still have the pi in here. So 120 pi, and the meters are squared here times meter to the 1 there, meter cubed. Is that all we did in this one? Seems kind of basic. Oh, look, my height got higher. There we go. A little bit smaller. That's it. Practice them on Schoology and practice them in IXL.